Energy Metabolism, Part 5, Beta-oxidation Reactions. In the last Chalk Talk episode, we learned that activated fatty acids are degraded in beta-oxidation. The enzymes involved cleave the fatty acid to form the 2-carbon unit acetyl-CoA. Cleavage occurs at the beta-carbon atom, C3, and involves 4 reaction steps. Are you wondering why fatty acids are broken down only at the head? Well, it's because the molecule has the required reactivity in proximity to the carboxylic acid group. The cleavage process repeats until the fatty acid is completely degraded. Let's take a closer look at these reaction steps. If you'd like to see molecular structures with the names of the substances, then click on Dieter's red molecule. You can hide the structures at any time by clicking on the molecule again. In the first reaction step, the single bond between the second and third carbon atoms of the acyl-CoA molecule is converted into a double bond. Do you remember episode 4 of our biochemistry course? We touched on how double bonds in fatty acids are indicated by Greek letters. The compound formed has a delta-2 double bond and is accordingly called delta-2 trans-enoyl-CoA. The term trans refers to the position of the adjacent hydrogen atoms and indicates that they are on opposite sides of the double bond. You should take note that this double bond has a trans orientation, which will be important later on. The enzyme responsible for this reaction step is acyl-CoA dehydrogenase. It may not be immediately obvious, but this first reaction step is actually an oxidation. To form the double bond, 2 electrons and 2 protons are transferred from the fatty acid to FAD. As a result, FADH2 is formed, which has a similar function as NADH and H+. We've encountered the latter before as a reducing equivalent in glycolysis. The cell can gain ATP from both forms of reducing equivalents in the electron transport chain. Therefore, we'll take note of FADH2 in our energy balance. In the second step of beta-oxidation, the enzyme enoyl-CoA hydratase facilitates the addition of a water molecule to the newly formed double bond in the fatty acid. This restores a single bond between C2 and C3, the alpha carbon and beta carbon atoms. However, the beta carbon atom of the fatty acid now has a hydroxyl group attached to it. The newly formed molecule is termed beta-hydroxyacyl-CoA. It's important to note that the reaction is a hydration and not an oxidation reaction, which might be suspected because an oxygen atom is inserted into the molecule. Now, in the third step, the fatty acid is further oxidized. The hydroxyl group at the beta carbon atom is converted into a keto group. The result is the formation of beta-ketoacyl-CoA. In this oxidation reaction, again, 2 electrons and 2 protons are removed from the fatty acid, which are now transferred to NAD+. In the process, the reducing equivalent NADH and H+ forms, which will also add to our energy balance. In respect to the reaction removing hydrogen atoms from the fatty acid, the enzyme responsible for this oxidation reaction is 3-hydroxyacyl-CoA dehydrogenase. Finally, in the fourth reaction, the thiolysis enzyme transfers coenzyme A to the beta-carbon atom of the fatty acid. This both cleaves the molecule and concurrently produces a new thioester, with the reaction accordingly called thiolysis. In this reaction, the first 2 carbon atoms of the fatty acid, C1 and C2, are cleaved as acetyl-CoA. The remaining fatty acid is an acyl-CoA shortened by 2 carbon atoms. The former C3, the beta-carbon atom, has become the new C1 in the shorter molecule. The acyl-CoA can keep re-entering beta-oxidation until 2 molecules of acetyl-CoA are formed in the fourth reaction step. Acetyl-CoA can be further broken down in the citric acid cycle. Let's look at the energy balance of beta-oxidation. Each cleavage of a C2 unit yields a total of 2 reducing equivalents, 1 FADH2 and 1 NADH and H+. In contrast to glycolysis, fatty acid degradation doesn't directly provide ATP. Nevertheless, fatty acids are a good energy store as they provide reducing equivalents to the electron transport chain to yield ATP, namely 1.5 ATP molecules per FADH2 equivalent and 2.5 ATP molecules per NADH and H+ equivalent. In total, beta-oxidation provides 4 molecules of ATP per cleaved C2 unit. However, this energy balance is only valid for beta-oxidation in the mitochondrion and does not apply to paroxysmal beta-oxidation. The FADH2 formed there is not transported into the mitochondrion for ATP synthesis, but is regenerated in the peroxisome under hydrogen peroxide formation. Therefore, paroxysmal fatty acid oxidation provides less energy than that in the mitochondria. Have you asked yourself the following on the beta-oxidation reactions? What happens to a fatty acid with an odd number of carbon atoms that can't be completely cleaved into acetyl-CoA? Also, what happens to fatty acids that possess double bonds? Well, let's go through the answers. For fatty acids with an odd number of carbon atoms, the final cleavage step results in a remaining C3 unit termed propionyl-CoA. This is then converted into succinyl-CoA, an intermediate in the citric acid cycle, where it can be further metabolized. For unsaturated fatty acids, the difficulty isn't the general presence of double bonds, but rather that they're usually in cis configuration. Let's go back and refresh our memory. The double bond formed in the first step of beta-oxidation is a trans double bond. The enzyme enoyl-CoA hydratase does not use fatty acids with cis double bonds as a substrate because of their conformation. Don't worry, we won't go into too much detail as the degradation of unsaturated fatty acids is rather complex. At this point, it's sufficient to note that unsaturated fatty acids with a cis double bond are broken down in the same way as saturated fatty acids until the cis double bond is in the delta 3 or delta 4 position. A cis bond in the delta 3 position can be transformed into a trans bond in the delta 2 position, which is then metabolized in regular beta-oxidation. For a cis double bond in the delta 4 position, an additional trans double bond in the delta 2 position is inserted, and the resulting dienoyl is converted into an acid with a single trans double bond in the delta 3 position. Through isomerization, this intermediate can be converted into a trans double bond in the delta 2 position so that the fatty acid can be further degraded by beta-oxidation. Let's move from biochemical special cases to clinical significance. You might be wondering where you'd encounter beta-oxidation in clinical practice. In fact, a malfunction in beta-oxidation rarely causes disease. They're genetic defects that become apparent during periods of fasting, that is, as a result of the ensuing glucose deficiency. The probability of surviving depends strongly on the diet of the affected individual. Their diet should be rich in carbohydrates, and fasting should be avoided. The most common condition associated with beta-oxidation is MCAD deficiency, which is due to defective acyl-CoA dehydrogenase. This enzyme is responsible for the oxidation of medium-chain fatty acids. Defects in the corresponding enzyme for very long-chain fatty acids can also occur. This condition is termed VLCAD deficiency. Another frequently occurring disorder is LCHAD deficiency, which is characterized by a defective 3-hydroxyacyl-CoA dehydrogenase. This enzyme is responsible for catalyzing the second oxidation of long-chain fatty acids. By the way, testing of the mentioned enzymes is part of newborn screening. Let's finish off with summarizing the most important points on beta-oxidation. The cleavage of acyl-CoA into acetyl-CoA occurs in 4 reaction steps. After the initial oxidation of the bond between C2 and C3, hydration takes place. Subsequently, the beta carbon atom is further oxidized. The final step involves cleavage of the molecule by thiolysis. In mitochondria, beta-oxidation results in one NADH and H+, and one FADH2 reducing equivalent per cleavage of acetyl-CoA. This corresponds to 4 ATP molecules. Paroxysmal beta-oxidation provides less energy as the FADH2 formed isn't introduced into the electron transport chain but is regenerated in the peroxisome under hydrogen peroxide formation. With odd-numbered fatty acids, a single C3 unit, propionyl-CoA, remains as a residual fragment. It can be converted into succinyl-CoA and introduced into the citric acid cycle. The double bond formed during beta-oxidation is a trans double bond. Therefore, the breakdown of unsaturated fatty acids with a cis double bond requires conversion into a trans double bond. Well, that's a lot of information to digest. If you're keen, try our quiz on fatty acid degradation on the next slide. In the upcoming episode, We'll look at what happens to acetyl-CoA in the citric acid cycle.